Ecology algebra class, we're going to take a look at the notes for section 5.4, which is working with logarithmic functions. Okay, so in this section we are going to evaluate some common log functions, evaluate logs with other bases. We'll look at natural log, which is base e, and maybe log base 2 is a common one they like to look at. Solve some basic exponential and log equations, solve some general exponential and log equations, and then convert between exponential and log form. Okay, so a common log is a log that's base 10. They refer to that one as common log. So the official definition here, it says the common log of a positive number x is denoted log of x, and it's defined by log of x equals k if and only if x equals 10 to the k power. Now, what that is saying, what we don't write, in certain expressions in mathematics, like for example, if it's a square root, it's implied that the index is a 2, right? If you have x, it's implied that the coefficient is a 1. If you just have log of x, it's implied that the base is a 10, okay? So that's called the common log. So if they don't have a base written there, it's implied that it's a 10. So the conversion between these two expressions, in the last section we worked with exponential equations. So logarithms is the natural follow-up to that, because in anything in mathematics, when we talk about a certain type of function, there's an inverse to that function. With arithmetic, when you learned addition, the inverse was subtraction. When you learned multiplication, the inverse was division. When you learned something squared, its inverse was a square root, right? And so since we learned about exponential functions, the inverse of that is a logarithmic function. Now the two are you can write log equations in their exponential form, and that's kind of what they're showing here. And the way that conversion goes, if you remember from Algebra 2, it's the base to the power that you're saying that log is equal to. So it's 10 to the k would be equal to whatever that value is, x. So that's what they're saying here, x equals 10 to the k power. So we'll put numbers in that and hopefully make a little better sense of that as we move along here. Okay. So again, they're making this connection. If you have x equals 10 to the k power, that means that log base 10 of 10 would equal k. And so if this is the case where you have a common log and then the base is also 10, they basically cancel each other out, and the answer to that would be just whatever the exponent is, k in that case. Okay, so some characteristics of the graphs of log functions. The y-axis is going to serve as a vertical asymptote. So the inputs, or the domain values, are numbers that are greater than 0, is what we're going to see. Okay, the range is actually going to end up being all real numbers. Okay, and what we noticed in the last section with the exponentials is that was reversed, and because they are inverse functions, that would be true. If we were looking at, for example, in the last function, y equals 2 to the x, we know that that's gonna, the graph is gonna look something like this, right? And so the domain is all real numbers, it's all the x values, but the range is just positive numbers. So when we start looking at inverses of those, so for example here, this is log base 10, it's the common log. So the inverse function of this one, actually, maybe instead of talking about 2 to the x, let's talk about 10 to the x, because that would be the actual inverse of this function here. And you can see, like, if I were graphing its inverse kind of beside it here, it would do something like this. But we would have that property of inverses, which is that they are reflections over the line y equals x. So when we talk about, we talked about exponential functions, and now we're talking about log functions, and they are going to have the properties of inverse functions the way that they do, which would be, one of them would be the domains and the ranges switch around. So here's some, just some common log expressions to evaluate. And the thing to think about here is, every one of these has a base 10 on it. And so really what you're asking yourself is 10 to what power equals whatever this number is, and in this case 10. Well, 10 to the first power is 10, and then you go to the next one. 10 to what power is 100? 10 to the second power is 100. 10 to what power is 1,000? 10 to the third power. So this is kind of how you and they're kind of showing you this over here. Okay, so these all could be written as powers of 10, 10 to the first, 10 to the second, 10 to the third, and so on, right? 10 to what power is 10,000 to the fourth power? Now if I had 1/10, right, that's the same as saying 10 to the negative 1. So the answer to this one's just negative 1. You know, 1/100th, that's 10 to the negative 2 power, right? So that's going to be negative 2 for that log value, and so on, negative 3. Now anytime you have a log base anything of 1, okay, so this one's always the same, regardless of if it's common log or if it was a natural log, I know what we're going to talk about. If you're taking log of 1, the answer is always 0. Now the reason for that is because anything to the 0 power, 10 to the 0 power equals 1. 2 to the 0 power equals 1. E to the 0 power equals 1. So log base anything of 1 is always going to be equal to 0. Okay, and that's what our answer is going to be the exponent of whatever that base would be to make it equal to this number. Okay, simplify each log by hand. So in other words, see if you can do it without a calculator. We just did this one. Log base anything of 1, that's always going to be 0. So for part A, that's 0. 1/1000th, remember, okay, so 1/1000th would be the same as 1 over 10 to the third, or 10 to the negative third. So the answer to this one is just negative 3. It's that power that's on the 10. Since this is, remember, these are all base 10 logs, right? Okay, this one here, it's log of 10 to the 1/2 power. A square root is like a 1/2 power. So our value for that is just 1/2. Whatever that exponent is. Now, remember we said that the domain for any log function is positive numbers. Now, the answer to this is no solution, or doesn't exist, because if you think about this, what you're asking yourself is 10, can I write 10 to a power? What we're saying is, so 10 to what power is going to equal negative 2, right? It's kind of something like I said it like this. 10 to some power has to equal this, and that power is the answer, right? 10 to what power equals negative 2? Well, that does never happen. You can't take a positive base and take it to some power and make it a negative value, right? So this is no solution, or does not exist. Whatever, you can put either of those expressions there. Okay. All right, moving on. And here we're talking about the graphs of, I kind of threw this out earlier, f of x equals 10 to the x versus, its inverse, which is log base 10 of x, right? These are just inverses of one another. And so since that is the case, they are inverses of one another, they'll have the, the properties like I talked about, where they're reflections over the line y equals x, and I did that sketch on a previous slide a little bit. Okay, so another inverse property of common log. Inverse functions basically kind of cancel each other out. So if I was taking the log of 10 to the x power, that's just going to cancel, it's log base 10 of 10 to the x. The log base 10 of 10 cancels and just leaves you with whatever that power is. And we saw that as we were evaluating some of these expressions here, right? So log base 10 of 10 to the first power is 1. Log base 10 of 10 to the second power is 2, and so on. That's kind of how we evaluated those. And then probably the less common way of seeing these expressions, but they will throw some of these at you, is if you have 10 as the base and then you have a log base 10 as the exponent. Well, again, they cancel. The log, which is the power, then cancels with the base that has that, because remember, this is a log base 10 of x up in there. And so then it just leaves you with whatever you're taking the log of, and in this case, they're just putting an x there. Okay, so they cancel each other out. Exponentials and logs cancel each other out as long as it's the same base, and these are base 10s. Okay, so, it doesn't have to be a base 10. If it's not a base 10, then they have to write what the log base is there. So this is log base 2. So in other words, so if we were thinking about what its inverse would be, if we're going to graph its inverse with it, if we were looking at 2 to the x, right, and we made like a table for that, we'd have numbers like, if we can input anything, we could put in -2, -1, 0, 1, 2, for example. 2 to the -2 would be like 1/4, 2 to the -1 would be 1/2, 2 to the 0, anything to the 0 is 1, 2 to the first, 2 to the second, and so then I would get like, I can't fit all that on there, but I would get something that looks like this. At 1 I'd be at 2, at 2 I'd be at 4. But it's going to be, you know, the inverse of this graph, having that property of reflecting over the line y equals x. And so if I wanted to graph this, I could just say, okay, well, I just flip all the x and y coordinates around to graph it, right? So if I wanted to graph its inverse, I could just flip these around. I could go 1/4, -2, 1/2, -1, 1, 0, 2, 1, 4, 2, and you know all of those points, you know, would appear on this graph right here of this log. Okay, so to generate a log graph, if you were doing that by hand, I would graph its inverse, its exponential inverse, because that's easier to do. We can easily calculate plugging 2 to some power and get those. But you know, logs are a little more foreign, so if we would generate this table, we just flip all the x and y coordinates around, and then we can create the graph for a log function. And then natural log graph looks very similar. The difference on this is that it's when we have ln of x, the base that's implied there is e. Now the number e, remember, is approximately like 2.7. We talked about that before. But that's, you know, it's an irrational number, so it's not a terminating decimal, but approximately 2.7. And it's going to be one that's used quite a bit, this natural log, with a base e, but so it's going to have a real similar shape. It's just instead of a base 2, it's base 2.7-ish. Okay, so this kind of gives us the way to transfer from a log equation into an exponential equation. And like I kind of do this, the a to the k would equal x. And I use that quite a bit when we start solving these equations as well. It's easier to solve something in this form probably than this form. So if you isolate a log expression on one side of the equation, then you can transform it into the exponential form and solve from that point. And I think I did refer to this a little bit too. The domain of a log, function or log base a is positive numbers. You can't input negative numbers, so it's 0 to infinity, positive numbers. The range is going to be all real numbers, negative infinity to infinity, and we saw that on these graphs. We have no negative x coordinates, so the domains are positives, but the range is all numbers. It's going to continue to rise as it goes off to the right like that. Inverse properties of logarithms, we touched on this as well, but now they're doing it for a general, any base a log. So log base a of a to the x, that would cancel out and leave you with just x. A to the log base a of x would just, again, cancel each other out and leave you with x, and we looked at that with the base 10 or the common log. Okay, so for evaluating these ones, what I typically demonstrate for students is I say, okay, we're trying to determine what this equals, so I make an equation out of it and say, hey, this equals something we don't know, call it x. And then that allows you to write it in exponential form. I would say, okay, I'm talking about 2 to some power, which is going to equal 8. So 2 to what power equals 8, and then, most of these that work out with a nice whole number, you can just do this mentally. We know that that's 2 to the third power, so x would equal 3, or the value of log base 2 of 8 would be 3. Okay. Now, on your calculator, there's a log, a change of base button on there too, where you can just type this straight in and get the answer. But you should kind of understand how this works. We're asking ourselves 2 to what power equals 8. It's 2 to the third power. The value for this. I guess maybe I shouldn't say x equals 3 because there's no x in this, but the value of this expression is 3, right? I think it helps to make it an equation and then solve for x by doing it this way. So now I'm asking myself 5 to what power equals 1/25th. Okay, so 5 to what power would equal 1/25? Well, we know 5 to the second power equals 25, and the reciprocal of that would be, we'd have to say then, it would have to be -2, right? So x would equal -2 because we know that 5 to the -2 power would be 1/5 squared, or 1/25. So -2 would be the value of this. If you're looking on your calculator, if you go to, let's see, I think it's under math, and then over to, it's A. All right. It might be a different, it's under math, but I can see it down here, log base or whatever, and it's under mine, it's choice A. But if we choose that one, it pulls it up like this on most of the newer software calculators. They have this on there, so I could do for example, the log base 2 of 8, I can just put the 2 in there and the 8 there and enter, and it gives me the value. If I was doing that other one, my math button, and then it was A, I was going to touch that, and then if I was going to do base 5 and then 1/25th, doing 1 divided by, I think that would, oops, 28. Delete, there we go, and enter, so -2. So you can check them on your calculator, that way you can use that math and then the log base button on there. Okay, so it says use inverse properties to evaluate each. So here, these are really straightforward because they're just showing us we have a log base 6, and then in my exponential expression here it's a base 6, so they cancel each other out. And the answer is just the exponent, so it's just -1.3. No work really to do, it's just recognizing, oh, I'm demonstrating a log with an exponential and that they cancel each other out, they're inverse functions of one another. Similarly here, this time it's the other way around. I start with my base 5, and then as the exponent I have a log base 5 of some expression x plus 8. So they cancel each other out basically, and I'm left with just, this is my answer, x plus 8. Okay, that's all we have to do there. I think I've already pointed this out, that the exponential function and its log counterpart are inverse functions of one another and have the properties of inverse functions. Every point, xy on one graph on its inverse would be y, the x and y coordinates would be switched around. So if 0, 1's on the 2 to the x graph, 1, 0's on the log base 2 of x graph, and in any other point that you'd see like that. If I have 2, 4 on the 2 to the x graph, then 4, 2 has to be on its inverse graph. Okay, and here we have e to the x and then natural log function, which has a base e. So again, just another example of a log and its inverse function and the properties that they have when you graph them. Okay, so example here where we're solving base 10 exponential equation. So what we want to do first is isolate. So there's no logs in here right now, but I think we have to use a log to solve it. And what we want to do is isolate the exponential part, which is the 10 to the 3x. So the first thing is let's divide by 4 on both sides of the equation. So then I'm going to get 10 to the 3x equals 244 divided by 4 is going to be what, 61, right? That should be 61. Okay, now what we want to do after this is where we have to use a log, because this isn't going to come out to a nice number, because 10 to no power, we know that if you take 10 to a power, you're just going to get numbers like 10, 100, 1000. You're not going to get 61. So it's going to come out to a decimal. So the way that we would show our work to evaluate this is we would take the log base 10 of both sides of the equation. So I'm going to take log, which is just common log. So usually you don't write base 10 because it's implied, but I'll just put it there to show for this example. So we're taking common log, which we know is base 10 again. Doesn't have to be necessary. Oops. Doesn't have to be really written there, but I'll just show it here. So I'm illustrating this just to show, okay, that property of that log base 10 of 10 to the 3x, they cancel and leave me with 3x on this side. Now I've got log, again, base 10 of 61. I'm not going to write base 10 again. So now to solve this, I just have to divide by 3. And this is going to be something, if we were going to give a rounded answer, we have to type this in a calculator. So log of 61 divided by 3 is how I'm going to get my answer. So I'm going to use the log button right here, log of 61, and we're going to divide that by 3. And so we get like 0.595 approximately. X is approximately 0.595. 5951. Okay, so we want to isolate the exponential part and then take the log base, whatever this base is, of both sides of the equation in that one. Okay, in the next example, there is a log base 10 in there. So let's isolate the log piece of it first. So we're going to divide by 5 first of all. So now I have log of 2x equals 16/5. Maybe I'll call that 3 1/5 or 3.2. A little easier. And now again, it's an implied base 10 because it is a common log, right? So I'm gonna, once I have it to this point, or if I have a log expression on one side and a constant on the other, change it into an exponential. So it's 10 to the 3.2 power is equal to 2x, okay? And so now it's all just, you know, constant on one side, 10 to the 3.2, that's a constant, equals 2x. And now I can just solve by dividing by 2, okay? So I would divide by 2, and I can type that expression into a calculator. I can say 10 to the 3.2 power and divided by 2, and I get 792.447, something like that, 0.45. So 792.447 approximately. Okay, so that's what we do on that equation. Couple others. So if I had, this one is it's exponential, so I'm asking myself e to what power equals 5. Well, that's not going to come out to, you know, e is already an irrational number, so we're going to probably need to use a calculator here. And so what we do here, because it's base e, that means we need to take the natural log of both sides of the equation. So you can take, you know, take a log of both sides of an equation. It's just, you know, it's a function. It's like, oh, I'm going to square root both sides, or I'm going to divide both sides by 2. You can take, you know, the log of both sides as long as it's the log with the same base. We're going to do an ln, which is base e. So that means if I have, you know, again, that's base e, so these guys cancel each other out. Now I'm just left with x on that side. So ln of 5 is really my answer. And if they said give an exact, you'd leave it like that, but we can get an approximate. We can just go to here and type natural log right there, ln of 5, and enter. You get like 1.609. Okay, so that's how we can solve that one. And part C, just like any other algebra equation, you want to isolate the piece that has the variables. So first thing is you're going to add 7, so you're going to have 3 times 2 to the x equals 27, and then you're going to divide by the 3. It's kind of like a coefficient there. So divide that. Now I've got 2 to the x equals 9, and at this point, if we want to get a, you know, a real close decimal answer by using our calculator, we'll have to use a logarithm now. We could estimate, you know, 2 to the 3rd power is 8, and 2 to the 4th power is 16, so our answer is going to be somewhere between 3 and 4, but if we want to get an exact value or something close to exact, we're going to take log base 2 of both sides of the equation. Okay, log base 2 of 9 then, because what happens here is that cancels, and then it just leaves us with x on the left side, and then log base 2 of 9, we can type that in. And again, that was under math, so I hit math, and this log, that base, choice A is what it is. And then I can type in log base 2 of 9 and hit enter. And I get approximately 3.1, well, about 3.17, I guess. Approximately 3.17. Now, I want to show you one other thing, just in case you're using a calculator that doesn't have that that change of base function on it. There's a way you could evaluate this without that, and the way that we would do it is, so for this one, you could take log of 9 divided by log of 2. So whatever the base is, you can just divide by that. So you can use like a common log 9 divided by common log 2, and divide it that way, and you'll get the same thing. So because everybody has a log button on there, so if I take log of 9 and divide that by log of 2, you should see we get the same values as what I had right there. Okay, so if you don't have that, a calculator that has this function in it, you can just divide those. Okay, and what else? A couple more. All right, so here it says we're just solving this log equation, and this one's pretty straightforward. I think all I would do here is I'm just going to change this to exponential form. 5 to the negative 2 power equals x, and that's just going to be 1/25 for my solution on that one. And let's see, is that all I have left? Okay. Let's see, then part, I wonder why I skipped part. That says B. C was up here. Well, okay. It's numbered kind of funny. Okay, so for this one, we've got 3 times log base 2 of 5, x equals 9. Okay, so we want to isolate the log expression, so let's divide by 3. Cancel that, so I've got log base 2 of 5x equals 3. And now at this point, I'm going to take 2 to the 3rd power. I'm going to write it as exponential form. 2 to the 3rd power equals 5x. 2 to the 3rd power equals 5x, and so that's 8 equals 5x. And let's divide by 5, and that should be our solution. So x equals 8/5. Okay, or I guess if you want a decimal, 1.6. And I think that's everything. So that's an introduction to solving some log equations, some basic log equations, and converting from exponential to log form, recognizing the inverse properties of exponential functions and log functions. So that's it for this.